welcome back student to our next class of complex analysis. In the previous class we learned a very important thing, and we find that if a function, complex function fz is given, and if I want to integrate it over some curve, so this is the plane and I want to integrate it over some curve a to b, then this integration, the value of this integration depends on only the initial and final value when this function fz is analytic. If the function is analytic, then this integration, which is over this line, is depend only on the initial and final value. We show few examples and show that if this function is not analytic, if you remember, fz is equal to z star, this function is not an analytic function. So, when we integrate this, we find that it depends on path. The integration fz dz, when fz is this z star, is depends on path. But if it is analytic, it is path independent. So, this integration, if fz is analytic, then it is path independent. This is a very interesting concept. Since it is a path independent, we should not bother about which path I am going, that is one issue. And another important issue that I like to mention today, which is equally important and very useful. So, this is, suppose this is my coordinate system, and I am going from this path to this path, a to b, and then return back from here to here. Okay, let me first do it in this way. This is path 1 and this is path 2. So, first I go a to b through path 1, and then I go a to b, this point b, through path 2. So, integration of over path 1 dz is equal to this, because it is a path independent integration. When it is possible, when fz, my fz is analytic. So, here fz is an analytic function. Now, from this we can write a very important and interesting thing, that if I write I, whatever the argument is here minus this, that should be equal to 0. That means integration of this, I take this integration to this side, and that should be equal to 0. Now, minus of these things is nothing but I am going b to a. So, that means I fz dz plus path 2 in opposite direction. So, if I put this limit, so it is a to b, and now my limit will be b to a fz dz, this is equal to 0. That means eventually I am coming back to my original position A. So, I start with here, I go here and return back to this. That means I am completing a closed loop. When I am completing a closed loop, what I find that my integration is 0. So, that means if I write here the total form, the complete form, that closed integral f z dz is equal to 0. That is a very important outcome that we find, and last year we mentioned about this equation. This equation is called Cauchy-Goursat equation. This particular integral form, if f z is analytic over some region, say this is the region where f z is analytic. Let me describe what is the meaning of this equation. This is the region where f z is analytic, and if I have a closed loop here C, and if I want to integrate this integration f z dz over this closed loop, so I will get the value 0. This is because this function f z, whatever the function f z I am talking about, is an analytic function. Now, we will prove that in more meticulous way, that how to show that. So, let us start with this. So, f z is u plus I v, and z is x plus I y as usual. So, dz is dx plus I dy. Now, if I want to find out the integration f z dz, it will be something like closed integration u plus I v this. I can rearrange this slightly, u dx minus v dy, this part, plus v dx plus u dy. I separate out these two integration like this, I just separate out. Now, the next thing is that now we are going to apply one relationship that we know, that if p and x is a function of x and y, p and q is a function of x and y, then we know the relationship that this is over some curve p dx plus q dy is equal to, post curve is equal to this quantity over the region qx minus py dx dy. We know this theorem very well. So, p and q, if they are function of x and y, and if this quantity is continuous, and if I integrate over some region C, then this quantity, this is the closed curve, and this closed curve is encircling some region, say R. So, that is why line integral become the surface integral. We use several time in the vector analysis, if you remember. Then this is the case. Now, if I try to apply here, then let us see how I get this. So, now okay, let me erase this part. because the blackboard is slightly small here. So this quantity and this quantity I replace through this theorem. So here I should write it u dx minus v dy. So that means here u is p and v is q, minus v is q rather. So that means I should write it here integration over some region, the region is enclosed by this circle, minus of v x minus u y dx dy. This is the first part, and second part plus I integration over this region u y, this u which is here, it should be u x minus this v will be v y dx dy. I landed up with this expression when I try to find out the total integration. So now I know that my function is analytic. So now you can understand, if my function is analytic, so fz is analytic, that eventually means that I have this relation ux is equal to vy or ux minus vy is equal to 0. This is one expression I have, and uy is equal to minus of vx. So uy plus vx, this quantity is also 0. This is true only for the analytic function. If this is true, then we can say the function is analytic. And now I have two expression. If I put this expression here, then you can readily find that this is 0. So here if I write ux plus vx plus uy, vx plus uy which is 0, so it is 0 plus, if I take minus common from that, then it will be vx plus uy, and this quantity ux minus vy, ux minus vy is this quantity ux minus vi, which is also 0. So if I put this here, then the real and imaginary part both are 0 individually. So that means this integration has to be 0. So this is 0, this quantity is 0. So that means the closed integration fz dz is 0 when fz is an analytic function. If it is an analytic function, then only we can say this is 0. The example we have already shown the last day's class. Another important thing I like to mention at this point, that we are talking about the region and all these things. So if a curve is like this, bounded some region, this is the region and this is the curve that I am talking about. Closed curve means it is bounding some region. So normally what happened that it depends on which direction I am going. So this direction is normally taken as the positive direction, because the left hand side is the region. Normally if the direction of this curve is such a way that it encircling the region, and this region is in the left hand side, when I move on through this curve, then this is considered to be as a positive direction. We need to use these things later, but this concept or this notation or this convention we should follow. Okay. So what we get so far, we get, let me write once again this expression, that fz dz is equal to 0 when C is a curve enclosing some region R, and in this region the function is analytic. So, fz is analytic in this region, fz is analytic in this region. Now, this is for this curve is a simply connected region. This curve is this is a simply connected curve, simply connected. Now, we try to find out what is the form or how this Cauchy-Goursat equation is valid for a multiply connected region, because multiply connected region is something which is different from the simply connected region. So, let us go back to our old class where we mentioned what is the meaning of multiply connected region. This is the region which is multiply connected. This is the annular region. Why? Because if I take any closed curve here, so let me remind you once again, if I draw a closed curve, this is say gamma is a closed curve over this region is annular region. Then what happened that if I want to shrink this YOLO curve to make a point, I want to shrink that so that this goes to a particular point, then what happened that I can't do that without going outside to the region. So, I need to go outside the region, then only I can do that. If this is the case, then this kind of region is called multiply connected region. This is multiply connected, and simply connected I have already shown. So, if this is a region and if this is my curve, some curve, closed curve say gamma, if I want to shrink that, it can readily come to this particular point without escaping the region. So, it will be inside the region and it will come to this point, it is collapsed to this point. This is a simply connected region, simply connected. Now, for this simply connected, I know this is true. When fz is analytic in this region, but if fz is analytic in this region, is this true, or how to show that it is also true for this multiply connected region, that we need to know. Okay. So, now let me draw a region somewhere here, say this is the region I am drawing, this is the region I am drawing. This point A, B, I am going to this, B, this is say C, and I am going to this region because when I go outside this curve, my region is in the left side. When I go inside, my region should be this side. So, the direction of this curve should be something like this. So, here it is D, E, F. This is the region I am talking about. This is a multiply connected region, and now I need to show that what is the form of Cauchy-Goursat equation for this kind of multiply region systems. Now, what we will do here that first I will make this region multiply connected region to simply connected region. How we will do that? So, let me first show you what is the concept of doing this. So, I want to replicate the same thing. So, suppose this is the curve. I am just replicating this one here, the same thing. What I will do that I will erase this part and make a, I will cut this and make a path like that. Please note carefully how the path is making. I am making this path. I make a small cut here so that I can have a path here. Now, this entire thing is simply connected, because if I want to have some region, this region can shrink and to collapse to a point. So, there is no multiply connected part is here. Only thing was this, I make a passage here so that this portion is now empty, and now I have an entire complete curve here, which is simply connected. And this is true, the Cauchy-Goursat equation is correct for simply connected, or it is already valid for simply connected region. So, I can make use of this concept here also and then try to find out how things is going on. Okay. So, that means I am making a cut here in this figure. If I do that, then I make a passage here like this. Now, if I write the Cauchy-Goursat equation for this case, the closed integral fz dz is equal to what value? A B C, A B C, I am going to this path, then again I return back to A, then go to D, then go to E, then F, then again D, and then A. Please mind it, this portion is infinitely narrow. So, this D point and this point are almost same. So, that is why I write it here D. So, it will come back to D point and then go to A point. This is a very narrow path, just I cut in a single line, over a single line, so that this become a simply connected region. So, this is the integration that I have in my hand. The closed path is now represented by A B C A D E F D A. This is the thing. Now, I separate out, because this closed path is made of many simple single lines. So, I can separate it out, these single lines. So, I can write that this is A B C A, this is one part of this integration, f z d z, this part, plus integration A B C D A, then A D, next part, only this strip I am talking about, this small strip f z d z plus D E F D E F D, I will return back to my D point again, and finally, I return back to my A point through the opposite direction. It is in this direction. Now, I am returning back to the opposite direction, please note it. So, plus integration of d A f z d z, this quantity is 0, this quantity is 0. So, once I have this entire thing and separate out these things, then I find one interesting thing, that one integration is here having AD and one integration here having opposite direction dA, this one and this one, the second integration and the fourth integration. So, this second and fourth integration, let me erase this, are opposite to each other. So, that means integration of AD fz dz is equal to minus of integration dA fz dz. It is a negative one, because it is for this integration it is coming A to D, and another integration it is coming going D to A, the opposite direction. So, when it is in opposite direction, so I can write this as this, that means the summation over AD integration plus dA integration is 0. That means in this total integration, this part and this part cancel out, this part and this part will going to cancel out. So, let me erase this part and erase this part, and finally, I have two expression in my hand which suggests one is A B C D A and another is D E F D. Now, there is no, the joining is not required because I have already derived these two circles. So, that means this is total fz dz is for this circle. If I say this circle is gamma 1 and this circle is, circle means this closed region, gamma 2, I should not say circle. So, this closed region I say gamma 1, this closed region I say gamma 2. So, this quantity is gamma 1 fz dz plus gamma 2 f dash z. That proves that this closed integral is basically true for multiply connected region also. This is the multiply connected region, and for this region I can say this is the case, which is equal to 0. So, we prove that Cauchy-Goursat equation or Cauchy-Goursat theorem is true for multiply connected region also. Now, the thing is that if it is it is the case, then I can write this as gamma 1 fz dz is equal to minus of gamma 2 fz dz. How the picture will look like here? Let me erase this. So, initially this was the picture. So, gamma 1 is in this direction, gamma 2 is in this direction. I am saying gamma 1 integration, whatever the integration over gamma 1, and that is equal to the negative of gamma 2, that means negative of these things. Now, if I reverse this sign, if I want to reverse this sign, this direction will going to be changed. Now, it is the outer circle or outer region, outer closed path is in the anti-clockwise, and if it is clockwise, then this clockwise should be represented as anti-clockwise by removing this sign. So, let me draw that clearly, then you will going to understand what I am trying to say. So, this is my one region and this is my another region. This is gamma 1 in this direction, and this is gamma 2 another region. So, integration gamma 1 fz dz. Now, I put a sign here for this closed integral, because this closed integrals now require this direction, is equal to minus of this gamma 2 fz dz, right. I am writing the same thing in terms of this new sign, which shows it is anticlockwise and clockwise respectively. Now, if I remove this sign, then what happened? This sign will going to change. So, I wanted to remove this negative sign. So, if I do that, then readily I can have. So, that means I will have the same sign in my hand. So, this, then I will simply have gamma 1 fz dz is equal to gamma 2 fz dz. That means, if I have a region here where the entire region, if my function is analytic, so whatever the equation, whatever the integration I have for this closed region gamma 1, the same value of the integration I should have if I put another circle inside that with gamma 2 notation. The direction is same. So, I will just replicate these things to these things. Gamma 1 is a bigger region, bigger closed curve, gamma 2 is a smaller closed curve. So, the integration value of the integration will be same for both the cases. Okay, with this I should conclude my class here. So, today we learned very important thing, that is how the Cauchy-Goursat equation is true for multiply connected region also, and we also prove the Cauchy-Goursat equation by using this Green's theorem and all these things. So, with that, let me conclude the class here. So, see you in the next class, where we will learn more about and going to use this Cauchy-Goursat equation to find out some integration or some integral form. So, with that, so see you in the next class. Thank you for your attention.